Hey everyone! Today I want to talk a little bit about machine learning. Let's say that you're a fresh data scientist and you're interested in machine learning. You've done your deed, you've taken some online courses here and there, you've done some regression, classification, or maybe even deep learning projects. And now you feel like you're ready to handle a client. And let's say that I am a client. Let's say that I am a healthcare client. And I've come to you with a classification problem. Let's say that I do breast cancer tests for patients, but I'm low on staff, so I don't have enough doctors to make the diagnosis. So I gave you my historic data, I gave you all my historic tests and their diagnosis, and I want you to make a machine learning model to predict whether a test is malignant or benign. And now you do what you do best. You go to scikit-learn, you import the best classification model there is, and then you do the most complicated part, which is .fit, .predict. And then because you're a great data scientist, you import an accuracy function to measure the performance of your model. And voila, you score an accuracy of 95% or above. For which I would love to say, great job. You have made an amazing contribution to our business. But there's one little problem that you missed there, and here is what it is. Because we're making regular precautionary tests to our patients, as you might have guessed already, the number of tests that turn out negative, which means that the patient does not have cancer, is just much larger than the number of tests that turn out positive, which means that the patient does have cancer. This is because obviously most people just don't have cancer. And this difference in proportions between the positive tests and negative tests is also referred to as imbalanced class distribution, which is a problem in machine learning when you want to predict two classes or more, but these classes just have different distributions. Now, why is this a problem? Let's try to think about this in an intuitive way. Let's say that you want to train a machine learning model to play chess, but you're making the model play white 90% of the time and only play black 10% of the time. Intuitively, you will just think that the model will just be better at playing white compared to when it's playing black. This is because the model is undertrained for playing black, and that's why it's performing poorly when it's playing black. This is not the only problem. Sometimes predicting one class correctly is just more important than predicting another class. I mean, think about it this way. Let's say that we predicted that a patient does have cancer, but they actually don't. I mean, this is obviously way less damaging than predicting someone to not have cancer, but they actually do. And so here, predicting correctly those who actually have cancer is much more important than predicting those who don't have cancer. And this cannot be measured by the accuracy, because the accuracy is just the total number of correct predictions over the total number of predictions, which does not really specify what we're predicting exactly. And this is why we need to use a metric such as recall. And the recall is measured per class, meaning that we have the recall for predicting the positive test, and we also have the recall for predicting the negative test. And here is how the recall is measured. It's just the true positive, which is the test that we predicted to be positive and they're actually positive, over, once again, true positive plus false negative, which are the tests that we predicted not to be positive, but they're actually positive. To put things into perspective, think about it this way. Let's say that we have 10 samples, 8 of which are negative and 2 of them are only positive. And let's say that we deployed the machine learning model to predict which is which. And the model ended up predicting the first 4 as positive and the last 6 as negative. This means that we predicted 2 values incorrectly. And 2 out of 10, that just leaves us with an accuracy of 80%. But for the positive class, we're still going to have a recall of 100%, because in the positive class, we are predicting all values correctly. Let's have another example. Let's say that the model only predicted the first value as positive and the remaining ones as negative. That means we're predicting the second value incorrectly. And 1 out of 10, that's just an accuracy of 90%. But for the positive class, we're going to have a recall of 50%. This is because we're predicting half of the positive class incorrectly. So the recall for the positive class is just out of our prediction for the positive class, how many actual positive values we've captured in our prediction for the positive class. Great job, everyone. So far, we've covered why machine learning models might perform poorly on minority class. We've also understood how the recall metric works and when the recall metric is important. But the question now is, how do you improve the recall for the minority class? And the answer lies under modeling imbalanced classes techniques. These techniques aims to change the distribution of the classes so they have equal presentation. And we can do this by either oversampling, which means that we randomly generate instances for the positive class so it evens out with the negative class. Or we perform undersampling, which means that we randomly remove values from the negative class until it evens out with the positive class. And finally, we can perform resampling, which means that we remove part of the negative class and we also randomly generate instances for the positive class so they can even out. Now, each of these techniques have their own advantages and disadvantages, and we also didn't go through the technicalities of how they actually work because that would make the video too long and too boring and I will end up just talking to myself. But maybe in the future I will make a separate video explaining those techniques and how to apply them even. In this video, there's another important thing that I haven't covered, which is the relationship between precision and recall and how they always correlate to each other. But I'll also make a separate video explaining that, because this video was just about tackling the hidden problem of imbalanced class distribution. Thank you very much for watching. I'll see you guys in the next video.